Looking for a fast-charging, ultra-responsive stylus for your iPad? Meet the 2X Fast Charge Active Stylus Pen, designed for 2018 to 2025 Apple iPads. Take your creativity and productivity to the next level. Click the link in the video description to shop now on Amazon.
Welcome to NASA News Network. I'm Emma, and today we're exploring one of the most fascinating phenomena in our solar system, the aurora. But what's behind those breathtaking displays of colored light? Let's dive into the latest mission from NASA that's shedding new light on this natural wonder. We're joined by Nellie Massavi-Hoyer, Program Manager of the EZIE mission at Johns Hopkins University Applied Physics Lab. Nellie, thanks for sharing your insights with us today. The aurora is a mesmerizing sight, but it's also closely tied to some pretty powerful forces at play in our solar system. Powerful streams of charged particles stream from the sun and hit Earth's upper atmosphere, exciting particles and generating those incredible colors we see as the northern and southern lights. For the first time ever, a trio of satellites called EZIE is studying how these electrojets work. NASA's EZIE Electrojet Zeeman Imaging Explorer will image and map electrical currents inside the aurora, called electrojets. Electrojets are high-intensity currents that flow 100 km above Earth's upper atmosphere, in the ionosphere, near the North and South poles. They push about 1 million amps of electric current around the poles every second. So why is this mission important? We're sending the EZIE satellites at the peak of the solar cycle, the approximately 11-year pattern of rising and falling activity on the sun. Electrojets are more active during the peak of the solar cycle, which means more opportunities to study their behavior. But how do we understand these electrojets? It's all about the Zeeman effect, a phenomenon where oxygen molecules create microwave emissions at 118 gigahertz. If there is a magnetic field close to these oxygen molecules, it will split that emission into multiple wavelengths. By studying the amount of splitting, we can calculate the strength and direction of the magnetic field that is affecting the oxygen molecules. It's like solving a puzzle. If you have information about the magnetic field, you can work backwards and find the current responsible for it. We have 3 CubeSats, tiny spacecraft the size of a suitcase, moving 10 minutes apart from each other. These are following each other in polar orbit at an altitude of approximately 550 km, 350 miles. The unique thing about this spacecraft is we don't have propulsion, we glide them. Imagine the solar panels as a glider's wing. We command the solar panels to move, and that helps us control the separation between the spacecraft. We need at least 2 spacecraft to understand how the electrojets evolve over time. By operating for 18 months after launch, though we think by the first 5 or 6 months we will answer all our key questions. Our goal is to operate at this perfect distance, and the sensors are exactly focused on what we're interested in. Until now, we didn't have the technology to do this. But with EZIE, we're getting closer to understanding the structure and evolution of the auroral electrojets and their impact on space weather. Electrojets are part of a huge electric circuit that connects Earth to space. These electrojet currents can cause sudden changes in Earth's magnetic field, sometimes leading to power grid disruptions and satellite issues. That's why scientists want to study them in detail. By understanding these currents, we'll be able to reduce the impact of space weather on our daily lives, from protecting life on Earth to helping astronauts in space. The EZIE mission is a groundbreaking achievement that's taking us one step closer to unlocking the secrets of the aurora. Thanks for joining me today and exploring this fascinating story with Nellie Massavi-Hoyer.